Hi, I'm Yaakov. In my day job, I'm a senior software developer at WiseTech Global, where we build the software that acts as the operating system for global logistics. At other times, I'm also a systems administrator for Smash, where we host an annual convention for all things anime and manga in years where there isn't a horrible, dangerous pandemic. But when, back in April, the Australian government announced a new app, one that they would position as a key requirement to lifting the lockdown restrictions and returning life to something vaguely representing normal, it got my attention. I have a bit of a history with reverse engineering things that get my attention, and last year I spent quite a bit of time breaking apart the New South Wales government's digital driver's licence app. So when COVIDSafe was released, I thought,
well, I guess that's worth a look.
And so it seems, so did a large portion of the tech community. Just a few days later, a bunch of high-profile techies held a panel discussion about the app after decompiling the Android version, and pretty much went, yep, it's all good, and then immediately moved on. Those who stayed behind for a bit of a deeper examination started picking up on other significant security and privacy issues, ranging all the way from a simple denial of service through to permanent tracking of users, with an exploit that got a CVE score of 9.8 out of 10 for just how critical it was. So, in the next 20 minutes, let's have a look at contact tracing and Bluetooth, how it works, and what it can and can't do. We'll dig into the COVIDSafe app, a bit of its history and how it works, and then look at some of the security and privacy issues, past and present. Lastly, we'll have a look at the exposure notification framework built by Apple and Google, and how that's different from the system that the Australian government has built. But first, a quick disclaimer. Despite having obtained my certificate of epidemiology from the Twitter School of Current Affairs, I'm absolutely not a medical expert in any way, shape, or form, so take anything I say on the medical side with a grain of salt. So, let's start with contact tracing. Contact tracing is the practice of figuring out who has contracted an infectious disease and who they may have spread it to. This is extremely critical when it comes to breaking the chain of transmission from person to person. Contact tracers, or disease detectives as the Australian officials like to call them, do this by talking to people who've tested positive for coronavirus, and then figuring out who they may have passed it on to, based on when they were contagious, where they've been, how close they were to other people, and how likely they were to spread it. Essentially, it's about getting ahead of the virus. If we can find people who may have contracted it, get them tested, and isolate them to stop them spreading it further, until we know that they either don't have the virus or don't have it anymore, then we can severely limit how far the virus can reach across our communities. This is why when you go to a restaurant, synagogue, hairdresser, barbershop, wedding, funeral, house auction, and more, they need to take down the names and contact details of everybody who has attended. If somebody who attends any of these high-risk places tests positive in the days that follow, contact tracers need to be able to pull up those lists and get anybody tested who they think is a close contact. Therefore, contact tracing is extremely important, though it's not entirely a preventative measure. In a similar way that uptime monitoring might go, hey, one of your servers is down, contact tracing also kicks in when it's too late, when somebody already has coronavirus. But if you distill contact tracing down to its core and then try to turn it into software, it doesn't need to be a potentially privacy-invasive process involving personal details. It doesn't need to know exactly where you've been or how long you were there, which can be a critical element of privacy for many people and their own personal threat models. Rather, they only need to know who you were with at certain times, and ideally in an anonymized manner, so that they can be informed, hey, you might have contracted coronavirus, but without knowing who they may have contracted it from, and without you knowing directly who you may have given it to, or vice versa. So really, what we need is just a way for people who you may have been in close contact with to be notified if you test positive. While we could exchange personal details over a local secure channel, that would require active participation. And unfortunately, people are lazy, and as we've seen, many aren't even taking the pandemic seriously. Asking everybody to actively keep a contact tracing diary is a big ask, so we need a passive system, which means we need some very strict privacy controls. Therefore, if we're going to automate this, consideration number one for privacy and security should be confidentiality. None of us should be broadcasting our personal details, and ideally, we shouldn't even be carrying around on our phones an identifiable list of people we've been around recently. That information should be confidential. Instead, we need some kind of anonymized identifier that gets exchanged between people's devices. Our other major concern is tracking. If somebody is broadcasting anonymized identifiers, I shouldn't be able to use these to stalk them, to figure out if they're home or not, or to track their movements over time. We've had enough problems with the advertising industry abusing static Wi-Fi and Bluetooth MAC addresses to follow people around, and we shouldn't be able to breathe new life into this. These are also both critical so that the public can have some confidence in the technology being used. If they're afraid of it, or distrusting of it, then they won't use it, and we may as well not have it at all. So, if we want to have a bunch of data exchanges between people, we need a technology that can do this. Ideally one that is already present on a device that they carry around with them at all times. And for this, there's really no better choice than Bluetooth. There are two kinds of Bluetooth, Bluetooth Classic and Bluetooth Low Energy. Bluetooth Classic is the kind used to connect to your car's entertainment unit, or your headphones, or to share your internet connection with tethering, and so on. It uses a relatively large amount of power and is a general pain when it comes to pairing devices, so that's not really our focus here. The much more interesting one for this use case is Bluetooth Low Energy, which is designed for short, occasional bursts of data. There are 4 modes called roles that it can operate in. Broadcast mode will simply broadcast some data to anybody that is listening. Observer mode is the opposite. It passively listens for those broadcasts. Both of these modes are connectionless. There is no active connection between the two phones. Think of it like Bluetooth UDP. If you haven't heard of this before, you might be an iPhone developer, as iOS limits this for system use. If you remember the iBeacons craze from about 7 years ago, those use these roles of Bluetooth to operate. The other 2 modes are central mode and peripheral mode. A peripheral is a device that waits for incoming connections, and a central is a device which connects to peripherals. Once 2 devices are connected, they can exchange data using GATT or GATT, the generic attribute profile. If generic attribute profile sounds like an overly broad term, that's because it is. It's just a way to define how the devices can read and write arbitrarily addressable pieces of data. In this structure, a device can expose one or more services, which in turn can contain one or more characteristics, which contain the actual data. For a concrete example of this, you might have a Raspberry Pi that monitors the environment. It might have an environmental sensing service, or weather service, which then exposes the temperature and humidity as 2 separate characteristics. These particular characteristics would likely be read-only, unless you're the Mossad and you can control the weather, in which case they might be read-write. The last thing we need to know about Bluetooth before we move on is how Bluetooth addresses work. There are 4 types of Bluetooth addresses, but as far as we're concerned, for consumer mobile phones, there are only 2. The other 2 don't get used here. The first one we need to know about is the public address, also called a static address. This is the hardware MAC address that is baked into your device when it is manufactured. The other is called a resolvable private address, or RPA. This is a second address that your phone uses to communicate, and the only one that it advertises. It changes periodically so that you become harder to track or stalk. This is the kind of thing that helps prevent the advertising industry from tracking your movements all around shopping centers. The resolvable private address is a function of the public address and an identity resolving key, or IRK. Your phones use both of these to generate a new private address, but this can also work in reverse. If you know the public address and the IRK, you can tell if any private address belongs to that particular device or not. This is why it's called resolvable. It can be resolved back to the original address, but only by paired devices. During pairing, or more technically, a process called bonding, 2 Bluetooth devices will exchange their public addresses and IRKs. That way they can always find each other in future. This is how, for example, your car can connect to your phone, even though your phone keeps changing its Bluetooth address. So we have a public address that makes your identity public, and a resolvable private address that helps to keep your identity private. Now that we know the basics of how Bluetooth works, let's have a look at how it was used. We start back in March with Trace Together, an app from the Singapore government that is designed to do exposure notification. I first heard about it from Asher Wolf on Twitter in the earlier days of the virus, at least here in Australia, when there were two apps starting to gain popularity. Private Kit, which I haven't heard of since, and Trace Together, which was later published as OpenTrace, and a copy of the code was given to the Australian government. The Australian government seemed to absolutely fall in love with this app and quickly rebranded it for Australian use. Scott Morrison said that the app, now called COVIDSafe, was like sunscreen.
Downloading the app is like putting on sunscreen to go out into the sun. It gives us protection as a nation. It protects you, it protects your family, it protects your loved ones, it protects our health workers, and it protects your job.
Sure, Scott, but only maybe, if it works. And initially, it didn't. Although the department responsible for the app, the Digital Transformation Agency, made this claim to the Senate.
this is implemented in a way that reaches the broadest range of the community in the shortest time possible, with the best protections for privacy, security, and delivering the best functionality possible.
Yet there were still numerous issues with it. So let's start by having a look at how this app actually works. We explained before how GATT allows Bluetooth devices to connect to each other and share data, and COVIDSafe uses this to exchange information. Essentially, COVIDSafe's first Bluetooth protocol was simply minor changes on top of OpenTrace. It ran the phone in both central and peripheral roles, but it used a different GATT characteristic ID to OpenTrace, so that OpenTrace and COVIDSafe would never see each other. Then, when a COVIDSafe central discovers a COVIDSafe peripheral, they exchange data by reading and writing a JSON value to each other. Your phone stores this value, and if you test positive, you can choose to upload your list of stored values to the server for contact tracers to use. The main thing contained in this JSON is a temporary anonymous identifier, known as a temp ID, that has been assigned to you by the back-end servers. This is supposed to change every 2 hours to make it harder to track you, and only the back-end servers, that is, the contact tracers at the Department of Health, can match this back to an actual person. It also contained your phone's model and your signal strength. The idea behind this is that since every phone has a different Bluetooth chip, if you can combine the phone model with the Bluetooth signal strength, then you can try and derive a distance reading from that signal strength and figure out how far apart the phones were. Aside from the fact that Bluetooth signal strength readings are unreliable as a proxy for distance even at the best of times, there were 2 big problems with this that the DTA later addressed. The first is that exposing your phone model can make you a lot easier to track. If you have the only iPhone 7 Plus in the room, then it makes no difference how frequently your Bluetooth address or your temp ID changes. You still stand out like a sore thumb. The other one is that the DTA seemed to be completely unable to actually make the temp ID rotate on a 2-hourly basis, or near enough. The code was inadequate at best, and would probably be better described as shocking. The iOS version and the Android version of the app were wildly inconsistent with each other, and the DTA, well, they basically gave up on fixing that. So they introduced version 2 of the protocol, which adds encryption to the messages. This time around, the app generates a new symmetric encryption key every 7.5 minutes. It encrypts the version 1 payload with this key, and then encrypts this key with the DTA's public key, so that only the backend can ever decrypt it. So on the surface, this doesn't sound too bad, and it sort of sounds like it does its job. So now, let's have a look at what went wrong. When COVIDSafe launched on the App Store and Google Play, it received an absolutely huge amount of marketing to encourage people to download it, both from the government as well as from private corporations. Probably the one that has aged the worst is a radio interview on 2GB with Rachel Falk, the CEO of the Cybersecurity Cooperative Research Centre, who said this.
Well, without going into detail, we certainly, with the Australian Signals Directorate and the Australian Cybersecurity Centre and DTA, we worked over 3 to 4 days, day and night, in shifts. But like all apps in development, you find glitches, you find things that don't work as well as they should. You find terms and conditions that when the app is operational don't actually always match what we say it will do.
I'd love to know what they found, because when the community got to analysing the app, both decompilation and source code analysis showed that it was almost identical to OpenTrace, just rebranded and renamed. There was absolutely no evidence of these 3 to 4 days of bug hunting, and everything that she has listed there, every type of defect, the community found multiple of these and more in the days, weeks, and months after the app was launched. There are a huge amount of general bugs. For example, background tracking on iOS did not work, because neither the Singapore nor Australian developers actually followed Apple's documentation on how to do background work correctly. Then, the Android version couldn't detect iOS when it was running in the background. After 2 hours running in the background, the iOS app stopped running because of bad error handling combined with incorrect security settings. The list just goes on and on and on and on, and if you want the full details, there's an impressive compilation on Vanessa Teague's blog on GitHub. But if you check out the government's own testing documents released to the Senate, they definitely didn't find any problems relating to security because they didn't even look. Aside from some other questionable items in their test plan, like items that recorded a pass but didn't record a result, if you scroll to the very bottom of it all, security testing is completely out of scope. Uh-oh. So let's have a look at a couple of the problems that the community found, but the DTA did not. The first issue is that various factors in the protocol enable users of the app to be tracked. If you broadcast multiple unique identifiers, changing just one of them does not throw off trackers. If I broadcast my Bluetooth address, temp ID, and phone model, and just the Bluetooth address changes, the other two factors remain the same, and you can easily reassociate the new Bluetooth address back to my device. Similarly, if just the temp ID changes, then you can reassociate the new temp ID to my device, since the model and Bluetooth address remained constant. And on Android, we throw the phone's name into the mix too, because Android publishes a GATT service that exposes your device name, such as Phil Coulson's top secret phone. If that's personally identifiable, then it doesn't matter how much your Bluetooth address or your temp ID change, you can still uniquely identify your device. Even on the version 2 encrypted protocol, although you'll get a new ciphertext every time, the portion of it that is the asymmetrically encrypted symmetric key remains constant for its lifetime of 7.5 minutes, so you can still track people straight through the encryption. And since there's no API on either platform to be notified when the operating system generates a new Bluetooth address, this is almost unfixable. The only way to solve this is to generate a full new value every single time, which would significantly decrease your phone's battery life. But the big dangerous issue is CVE-2020-12856, and this takes us back into how Bluetooth works. Essentially, GATT characteristics can also require authentication or encryption. That means that you can only read or write this characteristic if you're a paired device. And GATT-based exposure notification apps like OpenTrace or COVIDSafe will, by design, try and connect to every other compatible device that they can find. So an attacker could set up a fake GATT server on a Raspberry Pi or something, and when an app tries to exchange the contact tracing data, the attacker can return an error code for, hey, you need to be paired first. And surprise, surprise, your phone will start trying to pair. On iOS, it will prompt you, the same as for any other pairing attempt. But as the name shown in the prompt can be controlled by the attacker, you can make it say, COVIDSafe is trying to pair, which will increase the chance of a user allowing it. An attacker can also disable the numeric comparison pairing method, and by using the just works pairing method instead, it now looks pretty convincing. But on Android, this is completely silent. It won't even prompt you. It will just silently pair with the attacker's device. And as we mentioned earlier, the bonding process will give the attacker your public address, which never changes, and your IRK. So now they can track you wherever you go, even after you uninstall the COVIDSafe app. What makes it even worse on Android is that you can escalate this with BlueFrag or CVE-2020-0022. And an attacker can get remote code execution on most Android phones out there in the wild, about 84% of them. The attacker can also change their Bluetooth profile once paired to silently become a remote keyboard for your phone, or a speaker, or an audio remote, or just about anything else that Bluetooth can usually do. The DTA tried to patch this on Android by using reflection to trick Android into thinking that it's already failed to bond, so that it doesn't even attempt the pairing process. Unfortunately, this doesn't fix the social engineering aspect of it, and doesn't necessarily work in all scenarios. Additionally, this reflection hackery only works on Android API level 28 or below, but starting in November, all apps on Google Play will be required to target API level 29 or higher. So that's a problem with no good solution. Lastly, although the DTA has provided patches to try fix these issues and many others, Google Play is not reliably delivering automatic updates to people's Android phones. Both the community and the DTA are aware of this, though we don't know exactly why. But there's a strong chance that an attacker could still pull off many of these kinds of attacks, since there is no reliable guarantee that people are actually using the fixed builds of COVIDSafe. Though in the last couple of weeks we have seen Google Play pushing updates to people's phones, so they may have done something funny to fix this. Now, around the same time that COVIDSafe was being built, Apple and Google were working on their own cross-platform exposure notification framework. You may have even already noticed this in the settings on your phone. So let's now have a look at how that works, and how it's different to what we've discussed so far. Unlike COVIDSafe and OpenTrace, which are centralized solutions, exposure notification is decentralized. Instead of registering with a server to get your temp IDs, each phone generates its own temp ID. Every day it generates a new daily key, and whenever the Bluetooth address would change, it derives a new identifier that it exchanges with other devices. To perform the exchange, it uses Bluetooth broadcasts to advertise its own identifier, and by observing for other devices' identifiers. This does not use GATT, and no connection is made between devices. If you test positive, instead of uploading everyone else's identifiers, your device just uploads your own daily keys for the last couple weeks. All the devices periodically poll one or more servers for these keys, and will then check its own logs to see if any of the identifiers it has stored can be derived from one of those keys. If a match is found, the other devices will alert their users, and the Health Authority app can also notify the Health Authority about this potential exposure or spread of coronavirus. This framework has been widely adopted by many countries around the world because it's the only solution that can actually work on mobile phones. It's also the only one that can use broadcast and observer mode on iOS, which in Australia is roughly half of mobile phone usage. And it's also the only solution that can synchronize temp ID changes with Bluetooth address changes, so that users are difficult to stalk. Exposure notification also handles all of the low-level Bluetooth interactions for you, so it's difficult for a sovereign app developer to stuff it up to the same level that the DTA already has with COVIDSafe. Now, Australia hasn't adopted this seemingly for two reasons. One is that there are additional restrictions on apps that use this framework, such as not being allowed to use additional Bluetooth, which means that we can't have a COVIDSafe app that uses both the custom protocol and the Apple and Google one. Therefore, there is no migration path other than building an entirely new side-by-side app. The other reason is that the top medical officials seem to be getting bad information about how it works and where contact tracers are involved in the process. They seem to think that they can't get alerted when an exposure is detected, which is blatantly false. The Irish app, for example, already does this. So for now, although there's a nice and readily available solution to take away all of our problems, the government refuses to use it, and we're stuck with COVIDSafe. So, in conclusion, number 1, do not build apps that connect to untrusted GATT peripherals, as the operating system can do things that compromise users' privacy. 2, if the government makes technical claims about something, verify them. They probably don't know what they're on about, or they've implemented them badly and can't be blindly trusted. 3, COVIDSafe at best has delivered little value, and at worst can be extremely harmful, and all third-party solutions suffer from the same fundamental flaws. The Apple and Google exposure notification framework is far superior. If you're working on an exposure notification app that doesn't use this framework, switch. And lastly, involve experts in complex areas where you have unknown unknowns, such as Bluetooth. If you don't even know what you don't know, you will probably break things. And on that note, I want to give credit to the following people who've been studying the app for the past few months and putting forward recommendations to the DTA to make the app more secure, more private, and actually work, holding them to account. My thanks go out to Dr. Chris Culnane, John Evershed, Ben Frengley, Jeffrey Huntley, Eleanor McMurtry, Dr. Robert Merkel, Jim Mussered, Manabu Nakazawa, Richard Nelson, Hubert Stewart, Associate Professor Vanessa Teague, and Dr. Alwyn Tew for much of the material in this talk. Thank you all. Lastly, if you want to find more information on all of this, check out Vanessa Teague's blog on GitHub. Thank you.